Hello everyone and welcome to this lecture. In this lecture we talk about regular graphs which are very simple to define, and then we will first see some properties of the eigenvalue and the eigenvector, especially corresponding to the largest one, and then we will see what is a bound on the largest independent set of a d-regular graph. Okay, so let us start with d-regular graphs. So simple definition. So d-regular graphs are graphs where every vertex has the same degree. Okay, so for example, a very simple looking graph, maybe this one. This is also a regular graph where each vertex has degree 0, so I will call it 0 regular graph. Okay, then maybe this one. So this is a graph where every vertex has degree 1, so this is one regular graph. Okay, then two regulars are, let me play with some more, right? So this is two regular, and maybe I will draw one more. Two regular graph. Okay, two regular graph. Okay, and then maybe one more. So this is three regular graph. Very good. Okay, so very simple. So every vertex has the degree same. Okay, very good. Now let us see the largest eigenvalue or corresponding eigenvector. Okay, so let us see the theorem. Okay, so theorem is, let G be a d-regular graph. Then what can we say? Then, okay, the one thing is the largest eigenvalue is always d. Okay, so one thing is the largest eigenvalue lambda 1 equal to d. Okay, and what? The multiplicity of d tells d equals the number of components, right? Components. So for example here, so how many components are there? There are two components, right? There are two components here. So how many eigenvalues will be equal to 2 here? There will be two eigenvalues, right? Two eigenvalues equal to 2. Similarly, how many eigenvalues equal to 1? It will be 2 again, because there are two components. Okay, so very good. But before that, we have to prove that the largest eigenvalue is equal to d. Okay, the next thing is, okay, any eigenvector corresponding to d is constant on each component. Okay, on each component. Basically, it means that so suppose there are many components. It's a d-regular graph, and each component is again a d-regular, right? So then you see an eigenvector corresponding to the largest eigenvalue, which is d here, and then you see the piecewise vector of size corresponding to basically these components. So these piecewise vectors will be constants. Okay, so some different constants, but yeah, so very good. So for each component it will be a constant. Okay, so very good. So let us prove this. Very good. So yeah, prove. The first one is why the largest eigenvalue is d. Why the largest eigenvalue is D? Okay, the largest eigenvalue, if you see, I mean, we can prove it many ways, but one easy way was, we already know that the largest eigenvalue of any graph is always less than the largest degree and always greater than the minimum degree, right? So minimum degree, let me denote it by this. This is minimum degree, this is largest degree, okay, but both of these are equal, right? Because D is regular, so this is equal to D, this is equal to D, which implies there is equality everywhere. That means lambda 1 is equal to D, okay. And what about the multiplicity of this? Remember, the eigenvalues of G are nothing but union of eigenvalues of components. So eigenvalues are, so suppose this denotes the eigenvalues of set of eigenvalues of G, okay. So this is nothing but union of, let me write, union of eigenvalues of each component, right? Each component of each component, but each component is again deregular, okay. Each component is again deregular graph, so again there will be a lambda 1 as eigenvalue, right? Lambda 1 equal to D as an eigenvalue. But remember, why this basically there cannot exist? Because of this, because this could be so the largest eigenvalue is equal to D, we have just proven that, right? And the union of eigenvalue is nothing but union of eigenvalues of each component, right? And largest eigenvalue, we have seen earlier that it's always unique, right, on each component. So it will be, so the B will be eigenvalue of each component, and for each component basically it will be unique, D will be unique, due to Perrin-Frobenius we have seen the theory. So this is indeed equal to, so this implies that, so the multiplicity of D is equal to number of component, equal to the number of components. Very good. So very simple fact. In fact, we can prove something. And by the way, what will be the eigenvector corresponding to D? Okay, what will be the, so let me write it here. What will be an eigenvector corresponding to D? Okay, suppose G is connected, so how it will look like? Okay, if G is connected, suppose, in fact even if G is not connected, right, we can always say that all one vector which you can say is an eigenvector for D, okay. And by the way, this is an if and only if condition. If for D all one vector is an eigenvector, then the graph will be D-regular, okay. So the converse part, if you see, so this is DIY for you. Why this is true? Okay, so basically just by looking at D and the corresponding eigenvector, you can tell whether the graph is regular or not. Okay, very good. Now let us prove the second part. Second part is what? Any eigenvector corresponding to D is constant on each component. Okay, so let us take, if all one vector is there, then of course this is trivially true, right? It's constant on. Okay, so let us see more general thing. So yeah, the second part is this. Okay, now suppose Ax is equal to lambda 1x, which is equal to nothing but dx, right? Okay, now suppose H is some component, H is some component, a component, H is a component of G. Okay, so suppose this is a component, there will be other components, so others. Okay, so suppose this is H. Okay, now suppose C is, okay, C is some value from X. C is some value which is actually maximum of all Xi's, okay, such that I actually belongs to vertex set of H. Basically what you do, so this will be a bigger vector, right? So suppose this is X, right? This will be X, and inside this, suppose you pick some vector which is corresponding to H, which is corresponding, and out of this part you are choosing the maximum one. Suppose the maximum, okay, suppose this maximum, this is max. Okay, and now suppose that this is equal to C, right? So now let me cook two subsets from H. So those subsets are, so one set is actually VC, which consists of all the vertices such that okay, so this I actually is in I belongs to vertex set of H. Okay, so I is in here, right? I here, and such that Xi equal to C. Suppose this is this, right? So suppose this is some VC, okay, and then remaining this part is suppose VH minus VC. Okay, so now remaining part is VH minus VC, which is nothing but set of all vertices which again belongs to VH, okay, vertex set of H, but now Xi is strictly lesser than C. Okay, so strictly lesser than C. But now if you see that if this part is non-empty, if VH minus VC is non-empty, empty spelling mistake, is non-empty, then what will happen? Remember, this is a connected, this is a component, right? So there has to be a vertex I here and vertex J here such that there is an H. Okay, so there exists an edge Ij. So suppose let me write I, this is J, Ij, where I belongs to VC and J belongs to VH minus VC. Okay, VH minus VC. Okay, so now if you see that, if you just by this equation, how can I write? So how can I write? So dxi, so what will be if you consider here dxi sum? So dxi is what? Let me write this. dxi is nothing but here dc, right? Because xi I am choosing from H, right? Sorry, VC. I is VC, where every value xi value is C, right? So this is equal to this. Now this, just by this product I can write summation over all the neighbors of I, okay, and then xk, all the neighbors of I and then xk, right? And out of these neighbors, these neighbors, there will be a neighbor which is J, right? So this is nothing but xj, okay, plus what? Plus again I neighbors to this, but now this k is not equal to j, and then rest of this k, right? Now remember, xj is strictly lesser than c. Okay, so now if you see that xj is strictly lesser than c, and these guys are maybe some of them might be C, some of might be lesser than C. So, and how many of these are? These are D minus 1, right? These are D minus 1, and because 1 is conjugate by, so the graph is D regular, so I will have D neighbors, one neighbor is this, so remaining are D minus. So this you can write always is equal to C for this, not in fact equal to, in fact strictly greater than this, right? C plus D minus 1 C, right? So this is equal to CD. Okay, which is giving us basically DC is lesser than DC, which is a contradiction. Is a contradiction. That means our assumption was wrong. That means this part is wrong. Hence what? So BH minus VC is empty. Okay, this is empty. That means every vertex is in VC. Basically VC is whole vertex set of H, and which in fact implies that every entry is equal to C. Every entry is constant. Okay, entry answer, and the result follows, and the result follows. Very simple stuff. Okay, now let us move to a very interesting quantity, okay, that we call independent set, and we have already defined this in some previous lectures. Okay, so independent set is what? It's a set of vertices such that no two vertex in that set have an edge between them. Okay, and it's always challenging to find an interesting thing to find the largest independent set. What is the size of largest independent cell? Okay, for the D regular graph, we will now give a very nice bound in terms of eigenvalues. Okay, so let us give this. So let me write the bound. Okay, so theorem for a D regular graph G, okay, with the smallest eigenvalue lambda and G. Okay, any independent set has size at most so n divided by 1 minus D divided by lambda n. Okay, so lambda 1 G you may write. Okay, very nice. So in terms of the smallest eigenvalue, in fact the largest is by default D. So you are giving a bound on an independent set of a D regular graph. Okay, remember this is very difficult. I mean, there is no polynomial time algorithm for computing this. So let us give one bound, and what will be the proof? Let us start the proof of it. Very simple proof. Okay, so let S be an independent set of size k. Okay, size k, and I need one notation. Let 1k be the vector where the ith entry is 1 if I belongs to S, otherwise 0. Basically it means that there will be k ones in 1k, right, and rest of the place it is 0. For the other vertices it is 0. Basically size of 1k is nothing but n cross 1. So it's a okay, so very easy looking vector. Okay, so there will be k ones, right? Okay, very good, and these will be corresponding to the vertices in S. Okay, now let us define a vector which is this y, which is n times nk, n times 1k, then k times, this is all one vector, all one, Okay, now let us see. Suppose AG is adjacency matrix. Okay, so what will be this quantity? A transpose G. Now you must be now again realizing that what I will make use of. I will make use of those ratio, right? Yeah, ratio of the smallest eigenvalues and largest eigenvalues. Okay, so this is nothing but 1 K transpose, then K1 transpose AG times this. So let me first write, then I will solve it. Okay, K1n. Okay, very good. Then what? Oh, okay, let me again, I think I have to still continue with this calculation. K1n AG1, okay, I can simply write this as n times AG1K. Then what? Now you will see that this will be nothing but AG and K times AG. So this is nothing but, if you see, because in AG there will be D ones, right? So this will be nothing but D into all 1. Very simple step. Now let me open it a bit. So this will be, yeah, okay, n square. So this will be n square 1K, then AG 1K. Very good. This part is done. Now what will be this part? So this part NK, I am multiplying this with now this term. So this will minus NK for sure. And then D is also there. Very good. Now what is N1K transpose ND, because there are K, so this will be again K, so let me write K square D. And am I done? Am I done? Yes. Okay, so this is very simple. Okay, then I will multiply with this. So this is minus Kn. Okay, now 1 transpose AG, and then 1 transpose AG is what? Again, if you do that, there are N 1 ones, but in AG there are D ones. So this is again 1, so D will be outside, so 1 N and then a 1K. This will be again giving you K, right? So K square D, and then the last term is this. This is what K square D again, and then 1. Ah, wow. So K square Dn. Oh my god, everywhere there is a K square Dn. Yeah, but I can cancel these two. Okay, so now this will be equal to, yeah, but what will be this quantity? What will be this quantity? If you see that this quantity is nothing but summation over Ij, but these Ij belongs to S, right? Both I and J belongs to S, and then Ij, right? Aij. But there is no edge between any two vertices in AI, so this has to go to 0. So then in the next line I will write that this is nothing but 0. So this part is n square times 0 minus n K square D, which is equal to minus 1 K square D. Very good. Very simple term. Now let us see what Y transpose Y is. Y transpose Y, hopefully can I see directly? Maybe not. Let me write. So n 1K transpose K 1n transpose, then n 1K K 1. Let me do it quickly. So this part is very good. So this is n square, then K times K. I am multiplying the same case. I am multiplying the same K, n square K. So this is K. So K n square. Very good. Then what is this? Minus 1K, again K square, because n K, and this will be multiplied this again K, so minus n K square. Perfectly fine. Then what will be this? This will be what? N K, then again, wow, n K square. I hope I am not making any mistake. Yes, minus, yes, n K square. Now what about this? This will be plus K square n. Wow, K square n. This is clear, right? So I can cancel this, right? K square n, K square n. Okay. Now what will be this? Basically this means that nk times n minus k. Clear? Okay, very good. Now very simple. And next steps are very simple. If you see what is lambda n, lambda n is the smallest eigenvalue, so it will be always less than y transpose ag y divided by y transpose y, and we know this, what these are: n k square d divided by n k n minus k. Now hopefully everything will be right, so this will be equal to nk goes to this, so basically if you do this, minus kd divided by n minus k. Now the things will be quite apparent, but I want, let me write in terms of k, so this is nothing but okay, so let me do it for you. So the lambda n times n, then lambda n k is always less than or equal to minus kd, but I have to write k, right? So let me do, why not I choose k here, I bring k here, right? So this will be k d minus lambda n is always less or equal to lambda n n. Very good. So now this is k is, this implies that k is less or equal to minus lambda n times n divided by d minus lambda n. Oh, and now I can actually divide by both by n minus lambda n, so this will be nothing but n, you divide by minus, so this will be 1, right? 1 minus d by lambda. Very good. So we have now proven it. Okay, so basically any independent set will be, the size will be at most this. Okay, now let us see for what kind of graph this is very bad, or what kind of graph this is very good. Okay, for, if you see, let us consider KNN, right? KNN, complete graph on n vertices. Okay, complete graph on n vertices. Okay, what are its eigenvalues? The smallest eigenvalue is what? So eigenvalues of these are given by what? Square root of n into n, basically it is n, right? So eigenvalue are nothing but n minus n, right? So smallest eigenvalue, so lambda ng of this is this, right? And then let us see what will be, what this quantity, and what is, by the way, what is the independent set, largest independent set? Largest independent size here is what? S. S is equal to, largest independent is n, right? But what is this quantity giving? So the quantity, now here n is 2n, because there are 2n number of vertices, right? 2n divided by 1 minus d is n, right? D, degree of every vertex here is n, and lambda n is minus n, right? So this will be, this will be 2. Wow, so this is giving n. This is in fact giving the equality. Okay, basically for complete bipartite graph on both end side where there are n vertices, this is strict. For what other graph this is strict? What other graph this is? Think about it, and with this I am stopping this lecture. Thank you very much, and see you in the next lecture.